All right, so 5.1. So we learned we are learning joint PDF or joint probability distribution, right? So now we're gonna study marginal probability distribution. Okay, so marginal probability distribution. Okay, so marginal probability distribution. What is this? That's the under the assumption that we deal with the multiple random variable distribution. Whoops. Okay, so oh yeah, give me a second. I think Emily sent email to me. Okay, so oh yeah, so that's a good question. I mean, so yeah, Emily asked that do we need to buy a new access code for Willy Plus, or did it transfer over to this semester? Okay, that totally depends on what type of access code you did purchase previous the last semester. When you purchase the access code for just one term, that means one semester. I'm sure that was expired. But if you did purchase the access code for multi-term, I think you can use it. Okay.
Mine was just one semester, but it's still working now. So I think it lasts longer than it says.
Then did you see that? Okay, then let me see. Give me a second. Second. Give me a second. Oh yeah. All right, so here, do you have to see this one? Math 4340 FA20 mathematical statistics. If you see this one, when you sign up the website, then it works. Okay. Is it? So you purchased the just one term access code and then it worked. You think it worked, and then you see that topic, name of topics, course. Then yeah, sorry, I'm wrong. Yeah, so then I think you can still use the access code what you used the last semester. Okay. Is it okay? Hello.
Yeah, sounds good.
Okay. All right. Okay. Let me see this one. Sharing. All right. So margin probability distribution. So what is this? Yeah. So yeah, when we deal with the multiple random variable, probability distribution with a multi-random variable, when we want to figure out the probability distribution, individual probability distribution. It means that probability distribution dealing with only one variable out of multiple variable. Then how can you do that? That's the marginal probability distribution. Okay, so website. Oh yeah. Before seeing example, yeah, I need to go over this. All right. So the f of x. So we like this. Okay, f x. I think let's assume that we deal with the PDF. PDF or PMF probability distribution with the two random variable x and y. Then marginal probability of x, marginal probability distribution of x. Okay, of x. Okay, so this is the notation of the marginal probability distribution of x. Okay, it's defined by, in case of the continuous random variable. So x and y are continuous random variable. Okay, that means this is marginal probability, marginal PDF, right, of x. this is defined by the integral and then fxy, okay, and then x comma y, and then dy. What does that mean? So this is the joint PDF, right? This is joint PDF. Oop, DF. Okay. So and then we that means well, we only the take a sum of all of the probability while y is moving and the x is fixed. Okay. Keep in mind this. So the x is the input, right? Okay. So you see that here? Yeah. So here x is the input, so x is fixed for some specific x specific value of random variable x. We're going to take integral with respect y. So y is a moving variable, kind of. Okay. So and then for the this is continuous random variable. In case of we deal with the discrete random variable, then fx of x, this is equal to bx is small x, right? That is equal to sigma. Okay, take a sum of all probability. X is x, and then y is y. But see that the y value is moving from, yeah, moving, and then we take a sum. So this is discrete random variable. Okay. So this is the first one. That's the marginal probability distribution of x. The second one, the marginal probability of y, is this fy of y that is equal to integral fxy and then x comma y and then dx. Right? And then for discrete random variable fy of x, y of y, right? This is equal to probability that y is y. That is equal to sigma x. Probability that x is x, y is y. Oh, capital letter y. Sorry. Okay, for discrete random variable. Okay, then all right. So I mean, look at it. These are just we can use these the formula to find out marginal probability distribution of x or y as single the value of x or y. But what if we want to find the probability that x is between a and b? Keep in mind is we assume that what the number of random variables is greater than 1. Okay, so more than 1, I mean. Okay, so this is not the probability of dealing with a single variable. This is a probability of the probability distribution dealing with a 2 random variable, or more than, anyway, maybe 2 or 3. Okay, so now this is equal to, then actually this is for the a through b. I mean, in general, I mean, so let's say x and y are continuous random variable. Then this is equal to integral a through b, and then f x dx. Okay, so we use the marginal probability density function. Okay, this is m p d f. But now then what? We by definition of fx marginal PDF of x, this is going to be equal to integral a through b, and then negative infinity to infinity, and then fxy join the PDF, right? So comma y, and then dy. This is the definition of marginal PDF of x, right? I know. So why use negative infinity? Because that, the limits of integration of random variable y depends on problem. So okay, the dx. So now that is equal to integral a through b, and then negative infinity to infinity, and then fxy, and then x comma y, and then dy, and the dx. So all right. So eventually, when you find out, well, the probability of x between a and b, in calculus, you have to what? Evaluate w integral anyway. All right, see, it's the example. Okay, example 5.4. Let me share the screen. Oh. Yeah, right. This is right. Oh, wait. Okay. You can see that, right? So example 5.4, server access time. Before doing that, let's see example of 5.3. Okay. So now, here's a question. The joint probability distribution of x and y in figure 5. We saw figure 5.1 last time. It's yeah, where is one? Figure 5. Yeah, this is a figure 5.1. Okay. So this is a table describing, I mean, depicting the relationship between response time and the number of bar of signal strength. Remember that? Okay. So the response time is the speed of the page download, and it is critical for a mobile website, right? So response, as the response time increase and customer become more frustrated and potentially abandon the site for competitive. Okay. So now then, keep in mind this. So now just move back to 5.3. All right. So let's find out then margin or PD, actually here, PMF, right? Because X and Y are discrete random variables. So let's find a margin or PMF of 3, X equals 3. Okay, you see that here, f of X of 3. That means what? We find the probability that X equals 3. Then we're going to find the probability that X equals 3 for each Y value. Because Y can, what's the possible numerical value of random variable Y? 1, 2, 3, and 4. So we're going to find the probability that x equals 3 and y equals 1, 2, 3, 4, adding them up. This is 0.55. Okay. So now in this way, we can find a marginal PMF for each x value for each y value. That's so figure 5.6. That's the marginal probability distribution of x and y. Yeah. Okay. So give me a second. Here. Yeah. Let's see. 4, what is this? That means marginal PMF of y equals 4. Okay. Then we're going to find the probability that x equals 1 and y is 4, plus probability that x equals 2 and y equals 4, probability that x is 3, y is 4, and then adding them up, which is 0.3. So this is a marginal 0.3. That's the marginal PMF of y equals 4. Okay. So similarly, 0.17, 0.25, 0.28, these are marginal PMF of y equals 3, 2, 1. Okay, all right. And then what's it 0.2? 0.2 is 0.2 is a marginal PMF of x equals 1. Okay, so we add these the values. Okay, then that's going to be a marginal PMF of x equals 1. Okay, so 0.25, 0.55, these are a marginal PMF of x equals 2 and 3. Okay, now we see that. So marginal PMF of x. So I mean, so here, what? So the PF of x, when you see the sub-index x, that means the x, random variable x is fixed as a specific value, and then y is moving from, I mean, for we find the probability for every y value, possible y value, and then taking some. Okay. So now, and then see. Oh yeah. So we need to share the screen, right? Second. Back to see. Okay. Example 5.4. Okay. So let's see. Problem. Okay. Here's a question. For the random variables that denote times in example 5.2, calculate the probability that y exceeds 2,000 milliseconds. All right. So what's the example 5.2? Oh, yeah, example 5.2. This is example 5.2. Remember that? So the X denote the time until computer server connect to your machine, and then Y denote the time until the server authorize you as a valid user. Okay, so the joint PDF is given by like that. Okay, here. Okay, and then x is less than y. From this, we could figure out the domain. I mean, yeah, domain. This one here. Okay. So now we move to example 5.4. All right. All right. So, all right. Uh, how can I do this one? Working. Let me use this one. Okay. Oh, interesting. That works, but this one doesn't work. Why? I don't know. All right. So the f x y x comma y. Let me copy the join the PDF. There was 6 times 10 to the negative 6 power and the e to the minus 0.001x and the minus 0.002y. Okay. So then let me draw the domain. Because x random variable x and y represent time, so it should be positive. So we deal with so we just play on just first quadrant, right, in the xi plane. So random variable x, random variable y. Okay, that's the domain, right? But here we want to find out what probability that the x.
See what you're writing.
Oh,
it's like really fuzzy.
Oh, I'm sorry. What happened? Hey, come on. Hey. Okay, did it work? Hey, come on. Okay. Oh, no, it worked. Okay. All right. So we'll find the probability that what y is greater than 2,000, isn't it? Because the problem says that what calculate the probability that y exceeds 2,000 millisecond. Okay. So this is nothing but what probability y, and then yeah, we cannot express that one as using the f sub y then notation. Sorry. So this is equal to integral. Okay. The what zero what integral and then f. Let me see. Give me a second. What was this? Yep. 2,000. Is it right? 1950. Yeah. We need to figure out. Okay, so we need to figure out the limit of integration for x and y, satisfying this one. Y is greater than 2,000. Sorry. So 2,000 raised to 2,000. Let's say here's 2,000. Okay, 2,000 right here. Right. So then the limits of integration. I mean, the reason satisfy y is greater than 2,000 going to be this here too. This one. You see that? Okay. Then then we need to figure out the equation of the line, this one and this one. Actually, this is a piecewise function, right? Piecewise linear function. So remember that in calculus, when you wanna evaluate integral over the region bounded by piecewise function, then we have to divide the region, right? So I'm going to divide region like this here. So this is going to be rectangle. So limits of integration for x going to be 0 to 2000, right? 0 to 2000, right? 2000. 0 to 2000, and then y limits of integration of y going to be 2000 to infinity. Region 1. For region 2, the limits of integration for x going to be 2000 to infinity, right? The limits of integration for y going to be x to infinity, because the equation of that linear that line going to be y equals x. Remember that. So we divide the region is into two sub-region here. So for first, give me a second. For the first region, okay. So the inner integral must be 2000 to infinity, and then f x y, x comma y, and then dy, and the outer integral are going to be 0 to 2000, and then dx. Okay, so here you see that here the outer integral, both their limits of integration numbers, so you can switch them out. Okay, so you can switch the order of integrals for the for this one. The second term plus. The second term is what? Since the limits of integration for y is what? X to infinity. So unknown variable x is involved. So integral with respect y must be inner integral. Okay. So oops, it's integral. Inner integral. Okay. So x to infinity, and then for the outer integral, which is the integral with respect to x, gonna be what? 2000 to infinity. 2000 to infinity, and then fxy, x comma y, and then dy and dx. Okay, this is the integral over the second region. Okay, so yeah, so then okay, yeah, let's see first integral. Okay, so let me do this one quickly. Okay, because you can see the solution in the textbook. Okay, so since this is not the calculus class, this is a statistic, course. So I don't want to spend, time too much calculating the integral. Okay. So the first integral going to be what? 6 times and 10 to the negative 6. The integral 0 to 2000, right? And then entire derivative of the exponential term. Oh, can you see that? Entire derivative exponential term. With respect y going to be what? E to d. First one, by the way, we're gonna the breakup. This one as the e to the negative 0.001 x times e to the negative 0.002 y. Okay, and then what I mean is this one, then 2000 to integral, okay, 2000 to infinity, and then e to the minus 0.002 y, and then dy, close parenthesis, and then times e to the minus 0.001 x, and then dx. You can say that. Okay. So now then this is equal to, now what's the then we evaluate that improper integral, right? The entire derivative of the integral is going to be e to the minus 0.002 y over minus 0.002. And we evaluate this one at infinity and 2000. Okay. This is kind of short expression of the solution of the improper integral. Okay, but all right. So now and then this is equal to here, and then that's 1, and times e to the minus 0.001x, and then dx, and then here's integral 0 to 2000, and then 6 times 10 to the negative 6. Okay. All right. So, all right. So then this is equal to now. Yeah. So I believe you can evaluate this one, right? Okay. Then yeah, it's not that hard to evaluate the outer integral too. Okay. So because once you evaluate the that the integral, you're gonna get number, right? Okay. A number that certain some number times exponential term, take a integral, then you will get the point. This is gonna be equal to 0.0475. Okay. Keep in mind this. So now next one for the second term. So second term. Okay. So now then this is equal to what? 2000 the infinity. Oh, I forgot to bring out the constant term. 6 times 10 to the negative 6. And then what? Where? The e to d minus 0.002y, the x2 infinity. Okay, times e to the minus 0.001x, and then d x. Okay. So let's see, to infinity. Now then, integral, since the what inner integral is involved the x, right? The variable x. So we're gonna get the function of x, right? So then this is equal to 6 times 10 to the negative 6, and then 2000, and then infinity. And then as y approaches infinity, the exponential term approaches 0, right? Because of negative sign. So this exponential term is decreasing function, right? Because of negative sign in the exponent. And the y approaches infinity, then this exponential term approaches 0. Okay. So now, divide by minus 0.002. I'm sorry, I forgot this. Now we substitute x into y. Okay, minus, so we got this minus in e to the minus 0.002x over minus 0.002 times e to the minus 0.001x in the dx. Okay. All right. So we can combine these two terms. Okay. So then simplify it. I mean, they evaluate the outer integral. Okay. So then we're gonna get the the answer, right? So okay. So let me do this then. We got 6 times 10 to the negative 6 over 0.002, right, times 2000 infinity, and then e to the minus 0.003x, right, dx. So that is equal to what? 6 times, I mean, sorry, 6 times 10 to the negative 6 over 0.002, and then minus 0.003, and then, I mean, e to the minus 0.003x over minus 0.003. That's the entire derivative of that integral, right? Okay, and then infinity to 2000. Okay. So I'm sure that you can evaluate this one, right? That you're gonna get answer, which is 0.0025. 0.0025. Okay. So now, finally, what's the answer? We want to find out probability y is greater than 2000, right? That was equal to 0.0475. That's the value of the first term. This one, okay, which was a 0.0475, right? And then plus value of the second term, which is 0.0025. Okay, so the answer is what? 0.05. Okay, 0.05, which is 5%. Okay, so probability that y is greater than 2000 is 5%. So what's the y? Y denote the what? The time that what the machine the authorize the user authorize you as a user, right? So the probability that the time takes the machine, authorize you as as a user is greater than 2000 millisecond is just 5%. Okay, so then now next one is give me a second. Now, yeah, there is an alternative way, you see. So the alternatively, the probability can be calculated from the marginal probability distribution of y as follows. So let me go over this one quickly. Okay. So you see, let's see here. Let me see. Give me a second. Okay. So now we find out probability alternative way is this greater than 2000. That is equal to. So the 2002, we can calculate this probability using marginal PDF. So now this one from here, I mean integral and then Fy. Let me see. Fy of y, okay, and then dy, and then 2000 to infinity. Yeah, we can calculate that probability as like this. Can you see this? Oh, yeah. Okay. So now then, what is this? So we need to, we're gonna figure out this one first. Okay. So Fy of y that is equal to integral, right? Negative infinity to infinity. Let's just remind the definition of the marginal PDF or marginal PDF of y, which is negative infinity, the joint probability distribution x comma y, and then dx, right? So we know the joint PDF, which is and then what? Give me a second. Yeah, so here, and then give me a second. So first one, let me see. Here, I need this one. Okay. So what? First one, negative infinity can be reduced by 0 to y. Wait a minute. How come? Because so we want to find Fy y is you see the small letter y, lowercase letter y is a specific random value, numerical value, right? For the random variable y. So let's say y is right there. Okay. All right. Okay. That means x cannot exceed that number, that value, which is y. Okay. So here's 0 to y. So we want to find out what? This one. Okay. So 0 to y. Okay. And then let me see, x, y value. Yeah. Okay. So now fxy going to be 6 times the 10 to the negative 6. And the e to the minus 0.001x minus 0.002y and then dx. Yes. Since this is an integral with respect to y, so once we set the breakup exponential term in two terms, the e to the minus 0.002y can be considered as a constant, right? And then we bring it out. So now that is equal to then, this is equal to 6 times 10 to the negative 6 times e to the minus 0.0022y, okay, and the integral 0 to y, okay, and then 0 to y and the e to the minus 0.001x in the dx. Okay. Then let me see. So now, okay. So now this is equal to, yeah. So okay. So this is a 6 times 10 to the negative 6 and e to the minus 0.002y and times, and the antiderivative of the exponential term going to be e to the minus 0.001x over minus 0.001, and then 0 to y. Okay. All right. So yeah, calculate this. Okay. Yeah, I'm sure that you can, evaluate this one, right? Okay. This is going to be equal to 6 times 10 to the negative 6 times e to the minus 0.002 y times 1 minus, okay, what, e to the minus 0.001y. Okay. So let's keep in mind the y is greater than 0. Okay. So now, once we got the marginal PDF of y, then we're gonna plug in this one into the integrand. Okay. Then probability that y is greater than 2000. Okay. That is equal to 6 times 10 to the negative 6, and then 2000 to infinity, and then e to the minus 0.002y, and then 1 minus e to the minus 0.001y. Okay, ty. Okay, and then we evaluate this one. Okay, then this, you should get the same probability as what we got in previous method. Okay, so let me skip calculating this one. Okay, yeah. So now what about the mean and variance of the joint distribution? Okay, so joint distribution, the mean and variance of joint distribution. Okay, so now e of x, okay, so this is equal to negative infinity, defined by x times marginal probability distribution of x and dx. Okay, but keep in mind this. Why this? This is in for the continuous random variable. That's gonna be the integral of the joint PDF, right? With respect to y, right? Excuse me. So that is equal to negative infinity to infinity, the negative infinity to infinity, and the x times fxy, and then x comma y, and then dy dx, because that is equal to negative infinity to infinity. Okay, because we don't know the limit of integration for y and x. In general, we can say that. So in the joint PDF or PMF, I mean joint PDF, right? I'm sorry, not PMF. PDF, and then dy, right? Okay. So plug in this one into here, then we can get this. All right. So keep in mind this, and then so there's two ways, right? So you just use joint PDF, or you find out a marginal PDF of x, okay, and evaluate that integral. Either one, just fine. Okay. What about variance? V of x is equal to negative infinity to infinity, and then x minus mu of x square. What is mu of x? This is the mean of the joint distribution. Okay, e of x, and then fx, and then x dx. So yeah, what is this? That is what? This one, right? integral of the joint PDF with respect y. So plug in, that integral into here, then you're gonna get what? You're gonna get the negative infinity to infinity, negative infinity to infinity, and then x minus mu of x, and then square, and then join PDF, x comma y, and then dy dx. Okay, so now yeah, let's see one simple example, okay, in the textbook. So let me share screen. Oh, 1.6. Oh yeah, look at this here. Then let's find out the here. Let's find out the expected value of x. Okay, e of x. Okay. Then from here, the figure 5.6. Okay, let me just back to here. So in the figure 5.6, the expected value of x, that's going to be what? This is going to be sigma, right? Sigma x and the x times fx and the x, right? Okay. But x can be what? X means the what? X denote the number of bars of signal strength. 1, 2, 3, right? So x can be 1 through the 3, right? Look at this, right? So now this is equal to then 1 times fx 1 plus 2 times fx 2 plus 3 times, oops, sorry, 3 times fx 3, right? So what's the marginal, PM, in this case, PMF, right? So PMF1 is, in the table, it says that 0.2. So this is 1 times 0.2 plus 2 times, and then marginal PMF of 2 is going to be 0.25 plus 3 times, and the 0.55. Okay. All right. But you may wonder that what is the expected value of y? Then you change the letter. Expected value of y going to be what? Y times marginal PDF of y. Okay, this is equal to y times f, f join the PDF times dy dx. Okay, or dx dy. It should be dx dy, right? Okay. Also, the variance of y going to be y minus mu y squared times a marginal PDF of y. Okay, and the dy is equal to y minus mu y squared join the PDF and then dx dy. Okay. All right. So let me stop here. And then next time we're gonna continue to 5.1. So wow, I really this give me a second. Yeah, that's all about 5.1. All right. So now I'm gonna cover 5.2 next time. Okay. All right.